Hello, it's Scott Manley here. Back in August 2018, Parker's solar probe got off to a spectacular and fiery start on its journey towards the sun. And in fact, this may seem hot, but it is nothing compared to the environment in which the Parker solar probe regularly finds itself, getting closer and closer to the sun and getting very hot every time it makes a dive down into the solar corona. But to get there, it took the biggest rocket that ULA had, with an extra stage added on top for extra delta V, and then a lot of orbital mechanics. About a month and a half after launch, it had an encounter with Venus, which brought its perihelion down to about 25 million kilometers. From there, it has 3 perihelion passes, and we have all the data from those. And on December 26th, it's due to have its third encounter with Venus, which will bring the perihelion down to about 20 million kilometers. And that will mean that during the spacecraft's next perihelion pass, it will be moving at over 100 kilometers per second. 109 kilometers per second. But yeah, I mean, the data has been coming in, and they're now actually sharing data from the first 2 perihelions with the general public. Of course, the science teams have been working on it as soon as it became available. And the first really interesting results have been published in this week's Nature. There are 4 featured papers based on new data from deeper inside the solar corona than we've ever been before. So the first and most obvious instrument is the imager, WHISPER, the wide field imager for the Parker Solar Probe. And this points out sideways from the spacecraft. Obviously it doesn't point towards the sun because that would just blind it, it's not that interesting. This is looking sideways as it orbits around the sun. There's 2 different perihelion passes here. Obviously what we're seeing here is a lot more structure in terms of the solar wind very close to the sun. I mean, if you look, you can see clumps and other features in the plasma as it moves out away from the sun. But what I found interesting from this was that they looked at the dust. Now, the dust just reflects the light. And what they found was evidence that the dust in space starts to fade away as you get very, very close to the sun. This is just evidence early on. Now, we know that there's dust throughout the solar system. It's been measured. And what happens is this spirals down towards the sun because of something called Poynting-Robertson drag. In fact, you can actually see the dust from Earth if you're under the right conditions. This is the zodiacal light. And if you remember, a certain Dr. Brian May studied this as part of his PhD. Well, when that dust spirals down too close to the sun at about 10 million kilometers, according to the WHISPER instrument, the dust is evaporating, the dust is fading out, and there's a point probably within that where there is no dust at all, and all the atoms that made up those dust grains have evaporated and are now part of the solar wind plasma. So anyway, moving back to the corona, to the solar wind, scientists have been studying that for a very long time. This is a sequence from the SOHO spacecraft. It sits between the sun and the Earth in the L1 Lagrange point, and you can see these, flows radiating out radial away from the sun. And using the WHISPER camera, they were able to see a lot more structure that never really made it out as far as the Earth. There are details which essentially disappear the further they travel, and so getting right in close lets us see that information. But of course, being in there means you can measure things like electric and magnetic fields. There are ways to detect these remotely, but the spacecraft has the fields experiment. It has a magnetometer which sits up on a boom behind the heat shield, and it also has a set of voltage sensors looking at the electric field that extend out sideways from the heat shield, and these let us get in situ measurements. Another instrument that's really important for in situ measurements is SWEEP, the solar wind electrons, atoms, and protons. This is a Faraday cup and other instruments that essentially capture the atoms and measure their velocity and their distribution. So it's just basically sampling the quality or the material that makes up the solar wind. With this information, with the spacecraft flying through these winds, they observed switchbacks. So what this was is essentially the magnetic field was going away from the sun, and then as they flew along, a second later it would be pointing back towards the sun and then away from the sun. So the interpretation was that the flow was getting kinked. You see, the solar wind isn't just a steady flow away from the sun, it's happening at different speeds. And sometimes you would have a slow chunk getting caught up with it by a fast chunk, and that would of course mean the fast chunk is overtaking it, it twists the magnetic field around and creates these switchbacks. I believe they also found evidence that some of the really slow flows might not even make it out of the early corona and fall back. Now, we have seen things like this where we have a prominence that blows up a bunch of material, and then that material falls back onto the sun's surface. Now, that was quite a large event, but during the passes, they actually observed many, many much smaller flares, smaller energetic events that would throw out particles. A big part of this investigation was the ESIS instrument, the Integrated Science Investigation of the Sun, and you'll notice that there actually is the symbol for the sun. This is basically a pair of instruments looking for high energy particles off the sun, protons and alpha particles that have been accelerated by energetic protons to much higher energies than found in the typical particles of the solar wind. There's different sets of instruments for different energy ranges, and they of course get direction information and other clues that help identify the origin of these. So these energetic particles can of course be detected at Earth for very large flares. There's not that many right now. The sun is in a solar minimum phase. It's more quiescent. But because Parker's solar probe gets so much closer to the sun, it's able to detect these things that would normally be washed out by the time they got to Earth. And during its 3 perihelia encounters, the Parker solar probe has detected thousands of these miniature flares that would normally never have been seen way out at the Earth. Also, this mission has given us some clues about how the sun's solar wind and magnetic field transition from being trapped and rotating along with the sun to becoming this sort of static flows that we see out at the Earth. Parker's solar probe detected rotation of this solar wind 30 million kilometers from the sun, so it dipped into this region where the solar wind is still very much entrained in the sun's magnetic field and is co-rotating almost with the sun itself. The transition they've seen, it seems to happen much more rapidly than they'd previously expected, but this is really, again, a very cool observation. This to me makes it clear that Parker solar probe isn't just descending through the sun's upper atmosphere, it's descending into a region where the sun's magnetic fields and electric fields very much are controlling the movement and flow of the plasma that it is emitting. So anyway, many of these processes we have observed from Earth, and we've had some ideas about how they exist and interact close to the sun, but we haven't really been able to get down close and look at it. And now Parker Solar Probe is enabling us to get there and see this. And this is really important because right now, of course, solar flares, solar events can have an effect on the Earth. At the very minimum, they make very pretty northern lights. At worst, they can knock out satellites, they can damage power grids, and so people on Earth have a legitimate interest in the weather of the sun. And because we're now able to get a better idea of how these things interact close down towards the surface, we can see how these phenomena begin to develop, and hopefully we might actually be able to get some clues as to how to observe them, how to predict when an event is going to cascade into a giant flare. Right now, we only get hours of warning from spacecraft that are sitting at the Lagrange point between the sun and the Earth. We may see a flare, we may think that it's dangerous, but we don't know whether the cloud is actually going to hit us until we actually get it bumping into satellites that are between us and the sun, and give us the details on the cloud, because it's entirely possible these things will miss the Earth, and it's in fact far more common. So yes, Parker Solar Probe going boldly where no spacecraft has gone before, into the fire. Great, we're looking for a lot more data from this. I'm Scott Manley. Fly safe.